All life on Earth relies on the energy output of a star 150 million kilometres away from us, the Sun. Each time that 4 hydrogen atoms fuse together into a helium nucleus in the Sun's core, a mere 0.7% of their rest mass is converted into energy. But this is enough to produce a self-sustaining nuclear chain reaction at a temperature of more than 15 million Kelvin and a pressure of 340 billion atmospheres. This may seem an unimaginable inferno, but a Britest transformation map can be used to describe the main pp1 chain and 2 competing side reactions, both of which ultimately reach the same endpoint, a fully ionised helium nucleus, or alpha particle. In fact, all species present are completely ionised, and because of this, somewhat remarkably, the ideal gas law is applicable, even at the extreme temperatures and pressures involved. Driving force analysis can be applied to these stellar transformations to explore what controls the nuclear reaction rates in the Sun. Astrophysicists have the underlying science of this process thoroughly covered, but whilst there may be no truly new insights on offer here, as in many more earthbound reactions, driving force analysis usefully highlights some key features of the system for non-specialists. There is little evidence of interaction between the ion plasma, electron plasma, and neutrinos present. To all intents, they seem to act as separate but intimately mixed phases within the Sun's core. The between-phase mass transfer transformations familiar to Britest practitioners dealing with industrial processes just don't occur. Particles are created in the ion plasma and simply don't interact with it thereafter. We can safely say that nuclear reactions are very sensitive to temperature. We can see that escaping neutrinos have an appreciable cooling effect on the stellar core. Finally, we may expect that late in the Sun's life, the increasing abundance of helium nuclei will promote an increase in the rates of the pp2 and pp3 chains relative to the pp1, to some extent balanced by increasing neutrino cooling. You may have to wait a while to check out that last prediction. Despite fusing 500 million metric tons of hydrogen each second for the last 4.6 billion years, the Sun is expected to continue to do so for another 5 billion or more. Truly, the brightest and brightest star in the sky.